All right, time for coding. This stream is for entertainment purposes only. Today, as usual, we will attempt to solve some coding problem under 40 minutes. Maybe we will eventually, maybe not. Who knows? So let's see. Let's see what we got today. Pick one. Easy problem. We have two special characters. The first character can be represented by one bit, 0. The second character can be represented by 2 bits, 1 0 or 1 1. Now, given a string represented by several bits, return whether the last character must be a 1-bit character or not. The given string will always end with 0. I have no idea what's going on. Okay, bits 1 0 0. Now, given a string represented by several bits, is it array of bits? I didn't get it. So are those int zeros and ones? Okay, zeros and ones. Why it's not boolean? Whatever. Um, Now, given a string represented by several bits, return whether the last character must be a 1-bit character or not. And in this case is 1 0, so the only way to decode it is 2-bit character and 2-bit character, so the last character is not 1-bit character. I see. Maybe I don't still completely understand it. So, yeah, people don't like this problem. I think I got the idea. So the idea is you need to go through the string and check how many zeros it contains. Because the thing is, so let's create a very bad example. I'm not sure if I can do this, but I would imagine something like 5 bits. So let's see. So the simple example I have in mind is like this, right? So we think that we can return 2 digits at the end, right? The pattern is 0 1. But the problem is we have 3 ones. And the only way to decode it is 1 1, 1 1, and then 0. Now what if we have 0 1 1 0? It's still 2, but now we can remove all zeros, right? Not all, this one. So should we go in cycle? So what about this one? And this is 0, this is 2 bits, and this is 1 bit, right? So it should be true. So false, false, true. Still don't understand the key problem here. I mean, I can reverse the string, or actually parse it in reverse order and assume initially, so it always ends with 0, right? So we know. So we can just start with this one and check. If it's 1, then obviously now given the string return whether the last character must be a 1-bit character or not. The given string will always end with 0. And I would imagine there will be no such string that is not created by 0, right? So if this second one is 0, we return true. So the length starts from 1. If length is 1, then true, right? So we don't even need to consider it. So let's see. So we say if bits size less than 2, right, return true, or if bit size equal to 1, because now if bits bit size -1 -2, right, so the second element from the end equals 0, return true. Because it's obvious, right? Like in this case, there is no way it can be 2-bit character. Even if it's 0 here, there is no such character as 0 0. So we can actually do else if statements. So up to this point, we have at least 2 bits and it ends as 1 0. So now we need to check if it's a 2 bits or not. How do we do this? Okay, so let's initially assume that Boolean one bit equals false, all right? So we know that if it's 2-bit, that we need to start considering something like 4 int I equals 0, I less than what? Then bit size minus 2, so without last two elements, right? I plus plus. So immediately, if we have only two elements, then this is 0 and we never enter this cycle and we return 1 bit false, right? So like in this case, in example 1, it already works. So if we run the code, it will show the correct result. Actually, it will show it because of this, because we checked that this is 0, so there is no way to decode it. But now, the interesting question is, we know that or maybe it's vice versa. Let's start with bits minus 3 and until I greater or equal to 0, I minus minus, right? So because in this case I becomes negative if it's just two elements, so it's fine. So if bits I, right, so the third element equals 1, so then we know that this should be 2-bit operation going forward, right? So this initial is false. If not 2-bit, then 2-bit equals true, right? If it's 2-bit operation, and we start with false because we assume that third element Well, if it's 0, well, if it's 2-bit, then we obviously check and then the first one bits I equal 1. All right, then we say what? Then we say 2-bit false. 2-bit equals false. All right, so so we check if it's not 2-bit operation and we encounter the 1, it means that the preceding element should be always 1, because we have 1 1 2-bit operation. We don't have 0 1, right? So we say it's 2-bit operation should be if you're already in 2-bit operation, then the current bit should be always 1, because all 2-bit operation starts with 1, right? Now, if we are not in 2-bit operation, right? Or maybe let's have it like this so it's more clear. Else basically means 2-bit false and bits I no, we have one more thing. Let's have it here. Else if it's 2-bit operations, we're currently in 2-bit operations, but bits I equals 0, right? Which it shouldn't be. Then we return true. All right, so it means that the last bit at the end is 1 character. All right, else we return false. We don't need 1 bit. So the problem is with this situation when we have 2-bit false and bits I equals 0, right? In this case, we can either enter 2-bit mode or not. like if we switch here, right? This is exactly our situation. We encounter 0 bit, and 2-bit gate right now is turned off. Yeah, let's imagine it was 1, so we want to check. If it's a 1-bit thing, well, actually, if it's 1 but this is 0, then we already know that this cannot be 2 qubit, right? So it should be 2 at the end, assuming that the string is always correct. Right, so it's true. Sorry, so it's false. If it's 1, then we need to check if this is 0, right? Then, this is trivial, man. This is super trivial. You don't even need this check. Because that's how it works, right? We know that this is 0, so no doubts here. So we go to the first element here. If it's 0, we return false. If it's 1, we continue. We go to the second one. Now, if it's 1, so if it's 0, we return true. If it's 1, we continue. Now, if we encounter second time 1, then we continue. All right. If we encounter 0, or again 1, now we okay, so if we encounter 3 1s in a row, all right, so the last 2 is true. If we encounter, so how many digits do we know to 100% say if it's 1 or not? So to me, so it always ends with 0, right? Then we have, let's say 1 or 0. Okay, let me write it here. So 0, then 1 or 0. So it's like binary thing. But then we can have again 1 or 0. Here is 1 or 0, right? And it seems like we need 4. So it's 1 or 0, 1 or 0, 1 or 0, 1 or 0. So in this case, we encounter second 0, it's true, right? So it's true. If it's 1, now it depends. If it's 0, this is false, 100%. If it's 1, then we check this element. If it's 0, then it's what? Then 1 1 is a 2-bit address, so this is 1, so this is true. And if it's 1, then it's 1 1 and 1 0, because, or it can be 1 1, right? So I see. then all of these should be ones. Alright? If all of these ones, then we only check whether it's how many ones do we have. If we have even number of ones, is it means that the last element is 1 bit. If it's odd number, it means that the last element is 2. Alright, so it's %2 based on the number of ones we have. Or maybe not. So I still don't see the clear. I feel like every consecutive element tells us what to check next. If the next is 0 or the next is 1, right? So that seems like I'm not going to solve this easy problem under 40 minutes. Oh my god. But this is super confusing. I mean, this is like a lot of possibilities, right? All right. So having 0 basically terminates the search. Having 1 create opportunity. So if it's 0, we stop. If it's 1, we keep going, because now we can have either 1 1. But if it's 0, right, then we can have 0 1. So this should be 1 bit operation at the end. I see. But if it's 1 2, then can it be 2 or 1? So let's imagine the next one is 0 here, right? Then it depends if it's 1. Or 0. If it's 2 zeros, we can say 0 is also 1 bit operation, right? So like in this case, if it's 0, it still can be 1 bit operation here, so it's 1 0 at the end. Yeah, I don't see clear algorithm here. Unless we have 0, then we return true, that's it, right? But this, oh man. So the problem here is exactly when we not 2-bit operation and we encounter 0, right? Because if it's not 2-bit and we encounter what, it forces us to have 2-bit operation. So if it's 2-bit and it's bit 0, then we return true immediately, because we know that we can't have 2-bit operation in this case. So it means the initial one ends with 0 only, because we need to shift by 1 bit to have this 1 1, so this 0 can be cancelled out. So this clear. This one now, we are not into bit operation and we encounter 0. So now we can have both 1-bit and 2-bit operations, right? So if it's a 1-bit, then basically we can just continue. If it's a 2-bit, then so if 2-bit, if it's not 2-bit operation and we encounter 0, right? And let's assume this case again. We have, let's say 1 1 0 1 0, right? So we say this is 2, this is 2, but this is left with 1. So if it's 1 more time here, then yes. But if we don't have this thing, then we have to have 2 here instead, right? 0 and 10 to have 2 bits. Because if it's something like this, right, so it's, we start here, then it's, yeah, obviously, but then you can just cancel out it, right? And go to 10, then cancel out and go into 10. But what do we know is that if it's 0 right after this, we immediately return true. But if it's 1, 1 and 0 here, or 1 here, then there might be an options, right? Because it can be this, and we can cancel out this, or have this and this. Okay, so 0 1 1 0 is always 1-bit operation at the end, so it's true. But 1 1 1 0 is where we have the issues, right? Because in this case, so in our case we assume, okay, this is 1 0, right? And we go with this. So we encounter 1, we enter 2-bit operation, we have 0, and we return false, true. So this is 1 bit at the end, because we can have 0 1 2-bit operation. But if, let's say, it's something like this, do we want to enter 2-bit or 1-bit? Does it matter? So one simple thing is just assume that it doesn't matter, right? And If 2 bit is false, keep it false. Or let's say like this, right? Because then we need to split the string in two. So the string is 1000 characters. Can we just depth first search, sort of, through options? And then every time we encounter this unclear situation, we split it? Okay, let's depth first search. I don't care. So every time it creates, every time we chain like this, we create, oh man, the complexity is exponential in this case. Do we have a better option? I don't know. So okay, let's just create the thing here, right? Const vector of int as ref bits. Let's see, I, right, int I, and then bool 2-bit. That's all we need, I guess, I think. So what we do is basically this, right? But specifically, so we have this 2-bit, we have we don't need I, right? And we can say while I greater or equal to 0, then we do this, right? 2-bit false, and then I minus minus. So we go to the next iteration. Here we return, so we don't need to worry about it. Here we again decrement it as if it's not 2-bit, and it's equal 1, so we again enter 2-bit, we set it true. Now it's 2-bit false and bits I equals 0, right? So now we have an option. So we return DFS of what? Of bits I minus minus, right? And then either false, so we assume no 2-bit operation in the first case, and then we have another one, right? So after while cycle we return false, meaning that if we went successfully without hitting this situation, right, then we can have a 2-bit at the end. So now something about this return. So this is true. 2-bit operation is true in this case. Right, so we return true if last character has to be 0. Has to be. In this case, specifically, if this returns true, so in this case it has to be 0, and this has to be 0, right? So there is no way, so it should be AND. This is true, so both are true. So in both cases, no matter it's 2-bit or not 2-bit, it has to be true. So we return true. If at least one of these is false, so we might have 2-bit operation. All right, and all we need to do now, so we don't need this, we don't need this, all we need to do now is just to call DFS bits I initially equal to bit size -3. So if it's negative, we just return false and that's it. And is it 2-bit? Well, initially it's false, right? So we don't care. So initially, because we start with the third element from the end, so if we're already in 2-bit operation, it means it's always 1 at the end. We assume that we're trying to have this 2-bit at the end, right? False, and then we don't need anything here. We just want to return this. Return this. All right, so this is it. We are run out of time. Oh, I didn't see anything. Okay, whatever. That's what I did with the first session. So let's see if we still pass the test, though I would imagine we will, and then debug upon submission. Most likely, I would imagine we won't pass the because these can chain. So 2 to the power of 1,000. How many how many operations potentially we might have? Oh man, it will just die. Yeah, I doubt this is the only way. I think it should be simpler one. I just don't see the simple logic behind it. Deadly signal, right? Stack overflow and address. Seriously, with this one? So we took 0 element, it was false, right? So it's not 2-bit, and we have 0. Maybe we should say minus minus I. So it becomes -1, right? -1, false, -1, false. So it should be basically -1 is already false, so it's false. We return false, and it should pass it. Let's submit one more time. Maybe that was the issue. Alright. Now it output false, but it's actually should be true. So let's see what's wrong with that, right? So we have 1, 0, so we pass this initial check. We start with 1. We send 1 here. And we immediately see we are not in 2-bit operation. No. So we enter 2-bit operation. That it says false. Ah. So the thing is, if we're still in 2-bit operation, we return true. 2-bit. 2-bit. So we reach the end of the cycle and we're still in 2-bit operation. Then true, otherwise false. Here we go. Run code. Submit. Now it should work. Doesn't. Interesting. Let's see. So we have 1, 0. We start with 0. 2-bit is false, right? 2-bit is not activated. We say okay. 2-bit is not activated. We have 0. So let's say we go with this 2-bit operation, right? So we go to the 1 and we're in 2-bit. 2-bit is 1, right? 2-bit false. Subtract 1. We go here, no, that's negative. So we say 2-bit is false, so false. Yeah, I just don't see it. All right, let's see. See out. I equal I and 2-bit equal 2-bit. So we go with I equal 1, which is this element, right? So it's 0. 2-bit equal false. So 2-bit false and we encounter 1. So 2-bit should be true, right? Why this 2-bit remains false? I don't understand. So if 2-bit false and we encounter 1, we say 2-bit true, I minus minus. So we go to 0, 2-bit should be true. Is it because it's not internal one? Boo. 2-bit internal equal to bit. Looks super weird. I don't know why. 2-bit. Alright, and then 2-bit internal, 2-bit internal, 2-bit internal, 2-bit internal, 2-bit internal, 2-bit internal, 7 is minus 1, minus I. That's it. Doesn't look right to me that we have, okay, 1 to bit 0, but why 0 is to bit 0? If 2-bit internal. So if this is not 2-bit operation, okay, it's not 2-bit operation, and bits I equals 1. It's not, right? It's 0. So this is this case. Now we check that, okay, in this case we go I equals 0 and 2-bit false, correct. So we actually did this all for nothing. But whatever, let's still keep this one. So that's why it's false here, because we use this one, right? So it's false, and we say in this case 2-bit, no, it's false, and bits equal I. So we say 2-bit true, right? 2-bit is true in this case, all right? So we return 2-bit, yes, then we return true. Okay, so this is true. But to return true, in this case, this should be true as well. If this is false, we return false. But we know we do not enter this one. Why? So the output's true. Oh man, yes. Jesus. Int, let's say like this, int I equals, so basically I minus 1, right? This was a stupid mistake. Yes, we passed it, finally. Super stupid. I mean, I'm not quite sure why we have passed it, but it works. It's super slow, but it works. Submit. Four milliseconds, 9.7 memory. Let's see if we can get 4 milliseconds and 9.6. Oh man. Alright, I'm done. So this is the best result we've got for easy problem. So let's switch to the whiteboard. So we've got 100% for time complexity, although it's technically, I'm not sure if we can construct exponential one. But I don't like this, right? So we basically DFS, we chain by 2, so we have 2 scenarios now. So, and then if we chain within this scenario, we again have 2 scenarios, and it is this 2, so it's 4 scenarios. But seems like it passes, okay, so. Whatever. Exponential solution sometimes works better than polynomial. Depends on the problem, like in this case they work. That's important. Alright, so let's go to second dashboard. So we've got today, and again, so debugging was a little bit more than 40 minutes, but that's okay. So the main algorithm hasn't been changed, so the main algorithm was done in 40 minutes. So the time is 100. The memory complexity is 83. So the combination is 183. Or should we be a little bit more happy? Done. See you tomorrow.